This conference will now be recorded.
Hey everyone. So this week we're going to do the review of the test package design. The team has made really good progress, and we're also getting ready for the next phase to sort of plan for the next phase, which is the actual board and the test package. One of the things we're pretty interested in is raising some funding for the next stage. We've got the funding for the first stage reasonably set up. So Praveen, are you able to log in and everything?
I don't know what's wrong. Why you can't log in?
Looks he's having some network issue.
Okay.
Nataraju, can you bring up Nataraju? Can you bring up the PPT?
Yes, sir. I will bring up the PPT. 1 minute.
Yeah.
Do you want to
Praveen,
make?
can you bring up the PPT? Praveen, can you share the PPT?
Yes, I don't have access to share.
No, that's easy. I can fix that.
Actually, BP, you need to make a Praveen as a presenter.
Yep, I'm going to do that right now. Can you try now, please, Praveen? So while we're waiting, yesterday was Hot Interconnect, at least our portion of Hot Interconnect. Elad had a very nice talk on the Bow interface. If you're interested, I think registration is free. You're you should, if you get a chance, please check it out.
There's a hot interconnect. Is it that one?
Yep.
Yeah.
Wait, I thought I saw you online at Hot Interconnect. You weren't? That's another Mike Bartley, I guess.
Yeah, I was online. Yeah, I was online
Okay.
for the first. Yeah.
His talk was yesterday at 1:30, I think. So.
Hi, Praveen. You still can't see your screen, Praveen.
So then registration is free. Check it out if you'd like.
Hey,
Praveen,
Bobby.
yes, sir.
I'm sorry I joined late. Can you repeat which talk was that?
Yesterday we had an invited talk on the Bow interface at the Hot Interconnect conference. Okay, hey, Mike, I think Praveen's having screen sharing problems. Do you want to switch to Nataraju, or do you want to share and then he can talk, or something?
It's coming up.
Yeah. Can you make me as a presenter?
Yeah, I can do that.
Hello, BP.
You can't see your screen yet. No.
I'll tell you what, if one of you can email me the presentation, I can share my screen and you can talk to it too.
Yeah. Okay, I will send the presentation, Mike, to you.
Yeah, like you can do that too. If you got back.
I've got the first 4 slides, so why don't I just present them? I can share them now and we can get going, and then hopefully we'll get the slides. Does that work?
Yeah, that works.
My screen.
Praveen, can you send the presentation to Mike?
Yeah, I'll send and I'll forward on the presentation. Yeah. Can you see my screen or not?
Yeah, we can see your
Yeah,
screen.
we are able to.
Okay. Well, so we just wanted to first of all just give a quick overview of TESOL. There was you should be seeing the PPT. Is that correct?
We see a pitch deck for TESOL.
Yeah. Okay.
4 slides, not including the title, 5 with the title.
Yeah. Okay. So this is just a very quick overview of TESOL. So put some context on the work we're doing. So the people we're working with at the moment are based in India. It's our main region in India. Nataraja, you might want to go on mute when you're not talking. There's a lot of background noise. Okay. Yeah. So and Praveen and Nataraja are based in India. We're about 2,800 employees. And what we're split across designs, VLSI, pre-silicon. So we work with most of the semiconductor companies, designing chips, digital and analog mixed signal, test engineering. Where we that's where we're going to do the talk next week. That is around our test engineering and our known good die flows. PCB design, which is Praveen's team, and embedded systems. So we actually put together chips as well. So effectively all the way across the silicon engineering and systems engineering, with lots of, we sort of help people produce their silicon and make their systems out of those. And the fact that we've got VLSI and test means we put together a lot of strategies. So we're just working, for example, on one of our customers is putting together a system of about 18 chiplets in it, and with a bow interface as well. And we're doing the DFT test strategy for that, based on our knowledge of DFT and the test engineering, and trying to reduce the costs and get some redundancy in there so that they can get the yield as high as possible with minimal test costs. So they're the type of things we work on, this combination of DFT and test. And then we work across a number of what we would call centers of excellence, which is where we put together a lot of our R&D ideas, if you like. And we're a service company, we're not a product company. To always looking types of services we want to offer to our customers. And you can see here there's a lot of work going on in test engineering in terms of millimeter wave, PAM4, high performance, and system level test. System level test is now getting a lot more interest from people, because structural testing may not always get enough coverage anymore. Automotive, HP data center, and we do a lot of our chiplet work within our HP data center of excellence. Okay, and then you can see the PCB work there that Praveen and his team have been doing. Okay, so I'll stop sharing.
Can you maybe at the end of the talk, can you talk more about the 80 chiplet product? I mean, at least in general terms.
Yeah, it's obviously confidential, but yeah, I can tell you generally what we're trying to do there. So if I stop sharing, that means I can go. Have you received the slides yet or not?
I can see your slides.
No. Have you received the slides from Praveen yet or not?
Hang on, let me check.
Because that would be.
Give me 1 second.
If not, then I'll send them.
Mike is sent to you. Mike is sent to you only.
Yeah, but okay.
Do you want to just keep sharing your screen, Mike, and have your guys walk through it?
Yeah. Okay. Yeah, that would work as well. I sent them. Okay, I sent them to you, Bappy, as a backup as well.
Okay.
But I can open this up now.
Thanks for your patience, everyone. Tasaw's doing some really good work at both as a contribution of their labor and for the test package project.
Okay. Can you see that, Bappy?
Yep.
Okay. Actually, I'll see if I might be able to go in full screen mode. I just have to. It's going to let me share my other screen. Let's see if I can go into presentation mode with that.
I got it too, if you want me to try.
Yeah, that might be easier. Because yeah.
Okay,
Okay,
hang on.
And then Praveen is going to talk over it. Praveen, can we hear you or not? Are you still on mute, Praveen?
Hello, Mike. Praveen is having some audio issue. I will gone through this.
Okay. So you can, Nataraja, you can talk through the slides, can you?
Yes.
Perfect. Okay, thank you very much. So
And
you should be able to,
can you see my screen?
yeah, perfect.
Yes, BP. Thanks.
I'm going to go full screen and you just tell me to keep going forward whenever you'd like me to, please.
Yeah. Okay.
Hey, if
Thank you.
someone can take notes and just email them to me if there's any important points, then I can add them to the minutes.
Okay. Yeah. Hello everyone. Thanks for this opportunity to work with the ODSA project for giving the opportunity to Tazal. As a Tazal, we have almost 30 members team for working for package design. We are working for all kind of a package design with flip chip, wire bond, MCM, zip kind of all type of package. In this package, we are working on the only package design. This is totally two types of die with multiple hit options. With one is blue cheetah, another one is die matrix. Both the dies we are using a different configuration with blue cheetah to D matrix, and the length also we are varying with different length. Can you go to the next slide, BP? This is the yeah. This is the design. Is having 16-bit with 512 Gbps packaging, and also in this design we are using a single-ended routing. Even though the speed is more, only clock we are routed as a differential pair, remaining signals are we routed as a single-ended. I think this is different presentation. BP, can you next slide?
There may be the wrong slide. Maybe this is the old set of
This
slides.
is the wrong slides what you are sharing. Shall I share my screen?
Yeah, if you can. I think these are the first set of slides.
Yeah, please make me as a presenter.
Yep, for sure.
Yeah, sorry. That was version 1. It's version 2 we want. Not
That's
version
okay. I'm pretty excited at the progress we made. So
1. We have to keep the tenterhooks for a little bit longer.
Yeah, I can't able to share the screen.
I made you no, it says you're a presenter.
But
Just give it a second. It might be a lag in giving you the permissions.
I'm seeing that the entire screen window and the Microsoft Edge tab. But if you select entire screen also, that is not coming. The share option is not highlighted. I think, yeah, I got it.
Okay.
Now you can able to see my screen.
Yes, we can.
Yeah.
Yeah, it's good. Okay.
Yes.
You can go to present mode
Where-
on the right side, bottom right, like that. Full screen. Yeah.
let's see.
Presentation mode, the last icon. Yeah.
Yes, you can see, you can able to see the screen now.
Yeah.
Yep.
Yeah.
Yeah, this is the package size is 40 by 40 with two types of die with different configuration. We have done the different configuration with D matrix to D matrix, blue cheetah to D matrix, and blue cheetah to blue cheetah, and blue cheetah to D matrix, and blue cheetah to blue cheetah with a different length as well as different uh, direction. If you see this is a 45-degree placement with 5 This is 5 with straight connectivity for all the chips. This is for 40 by 40 with 1 pitch BGA, and also we are using a lid for heat sink as a heat sink. This is the heat sink area. Next. Okay, this is the overall package details. We have a total 10 dies, 6 blue cheetah and 4 D matrix, and this is the TSMC technology with 12 nanometer for blue cheetah and 6 nanometer for D matrix, and die size is 2.5 by 2.6 for blue cheetah, and D matrix is 1.284 into 3.246. The bump pitch is for both 130 micron, and we are done this design with 5 to 5 build-up layers stack up, and the package size is 40 by 40 For build-up layer, build-up material we are using GL102. Here totally 5 sites are there, and we have the decoupling capacitor placement for all the power supplies. This is the stack up we are using. In this stack up, we are done the routing in second layer and fourth layer for all signals with the reference of both the sides. For second layer, top layer and third layer as a reference, and fourth layer, third and fifth layer as a reference. And power and all those things we are routed in downside of the core. This is the in configuration of die. We have a RX TX signals like in blue cheetah. This is the RX and TX configuration, and this is the D matrix configuration. In the D matrix, we have 4 slice with RX and TX. Between power is there, and this is the overall routing we are done for this package. Yeah, actually here we are done the routing. The challenge is all the 64-bit routing we are done with single-ended, and only clock we are routed as a differential pair, even though the high speed signals, and this is say is done by some other person, but everything is passed. For achieving the SI consideration, we are giving the solid reference for both the sides, as well as near to the bump we are giving the guarding for all the signals. This is the 45-degree routing, and here the only this configuration we can't able to achieve the length. All other uh, routing we are achieve the length without doing any length matching. We are achieving the length with less the skew is 0.5 only this we can't able to achieve because of the this 90-degree, this SI is going on. If anything we need to do the length matching, we have to do the length matching only this configuration. Hello, this is taking time. Everybody hear me?
Yep, we can hear you.
Yeah. Sorry for slide that is taking some time.
Maybe it's got a pretty heavy
Yeah,
graphics or something.
yeah, graphics is more, that's why.
But you can start talking to it and when it paints. Yeah.
Yeah. Yes, you can see this routing. To achieve the same length, we are doing the zero angle routing for BCM to BCA to DM, because these die sizes are totally different. That's why we are doing with a zero angle routing with the guarding for some signals wherever possible. We are giving the guarding, and also we are not doing any length matching. We are achieving the length, but difference is very less. This is the 5 mm routing. The same is we are done with 5 mm. Here we are done only 32-bit because of the configuration. The both the die configuration is totally different. That's why we are achieving only 32 bit data. Other one we are achieving the same die, means we are achieving with 64-bit data. This is the BGA assignment we are done. Here what we are done with, we are tried in the PCB we can able to done the routing in 2 layers. That way we are assigned only 4 rows of all corner. We are used the right side and left side corner, only 4 row we are used. This will help to reduce the PCB layers.
So the previous slide, if you don't go back to it since it's such a heavy load. Oh, okay, that
Yeah.
works. This is on the left is D matrix and the right is blue cheetah.
Yeah. Blue cheetah to D matrix.
Blue cheetah to D matrix. Okay. And the 60, this one is, and JP chose all of these options effectively. The one this is being, oh, very cool. Thank you.
Yeah, this is 20 mm length. This is 5 mm length. For SI consideration, as I told, we are done with a good reference for both the sides for all the signals, and also in the bump shielding near to the bump we are giving the routed shielding to all the signals to segregation between power and signals. The skew length is, even though we are not done any length matching, the clock to data signal is less than 5 mm, 0.5 mm, sorry. And in the regarding the power, even though the power is very less, we are giving the solid reference for power, low inductance path, and separation between the power to power. We are taking care in this design, and also decoupling we are taking care. In the decoupling capacitor, we are placed exactly below the die to achieve the lesser return path as well as lesser length for, and also that BGA ball also very near. You can see here, this is the BGA balls exactly above the die pins also there, the power pins. We are removing the balls here and we are placing the decoupling capacitor. Here the PA consideration, as I told, we are taking care about the uh, decoupling things, and also the power, all the power we are giving the suppression with ground. You can see here for all the powers we are giving the separation with the ground.
So like shielding, you have
Yeah,
provided the
shielding.
ground between. Yeah.
Yes, we are
So
giving the
isolated
shielding
the.
for all the powers. Challenges here faced earlier is once we start this, the power routing with different configuration, and finally we are achieving all blue cheetah is one side and D matrix in one side. This is very useful for segregation of power and signal powers. You can see all four D matrix in one, this half of the diagonally half of the PGA and remaining BCA, the blue cheetah dice are one side. This for getting this we are done some iteration. This is the power routing because of the signals between the power we are done with a very smaller trace to achieve the connectivity of the power. You can see here we are giving this ground shielding for all signals, and also the stub length it is very less. And one more challenge we are faced in this, we have a 10 die to make the net list for connectivity a little bit challenge. In this we are done with the die TX to RX, which is the TX the first, then RX is the next name. Like that we are taking and we are given the net name for all and achieve the net list. And also here the one more challenge is the decoupling capacitor placement for achieving the better decoupling thing. We are done a lot of iteration for ball assignment and decoupling placement, and finally we are achieved, we are removing some balls and we are placing the exactly below the die the decoupling capacitors. Yeah, thank you. Have any questions?
Thank you. This JP, this seems like real progress. So, hey, what was the motivation for the right angle? More like, was that a JP's ask?
Hi, Bobby. This is JP. Yeah, the right angle was one of the use cases that all the companies participating were requested. So this is one of the real use cases we want to try it out, because the challenge there is the skew is not compensated. The skew, it has a higher skew than the regular straight line configuration. So we want to validate that 90-degree bend because it seems to be a common chiplet use case.
Got it. Thanks. So the use cases here are the sort of the right angle and varying distances and the interoperability.
That's correct. Yeah. The the distance are based on usage length, the min and max.
All right.
I
Thank you.
have a question. I have a question. Can we go back to the package model overview page?
That's for Natraju. Would you
Yeah.
mind sharing your screen again?
Or maybe I'll just ask my question. So for Blue Cheetah, you
Yeah,
have different orientations, but for D-metric or D-matrix, you only have one orientation. Is that correct?
yes, only blue cheetah to blue cheetah we have a 45-degree placement.
Different orientation.
Yeah.
Or is it just placement? Well, you have different orientation too, right?
Yes.
Yeah.
Yes.
Okay, and the other one is only one orientation.
Yes. Yes.
Okay, okay. I just want to confirm that. Thank you.
What is the total number of pairs? It's a 4 pairs we're seeing here.
Yeah. Totally 5 pair.
Oh, okay. Below. Okay. Okay, so we're interconnecting die with very different aspect ratios and very different pin layouts.
Yes.
Okay.
Yeah.
Any other questions? JP, do you want? Is there anything you want to share about the test package?
Yeah, Bobby, I want to mainly talk about the test bring up PCB.
Thanks, Nataraja. Thank you.
Yeah.
And
So,
Thank you. Thanks everybody. Shall I stop my sharing?
yes, please.
Yes.
yeah, thank you, Nadraju and Tasol team. Very good work on the package development. And I think currently the package layout is completed. We're working on the electrical validation, the signal integrity, and power integrity. We'll do we'll do an update on this later time about particularly on the electrical validation. There are a lot of interesting things that came out. In today's actually we have about 20 minutes. So I want to talk about the Bring Up PCB platform that we are working on. Let me share my screen. So I hope you can see my screen.
Yep.
Yeah, the main reason they're working on the package and Bring Up PCB is all about establishing interoperability. And since we expect the chiplets to be sourced from multiple vendors, interoperability becomes the key. And in fact, this came out of a real need in one of the meetings, and that's how they started this work on interoperability validation of the BOW interface. In the phase one, we'll be focusing on the PHY level interoperability, and later on, we're moving along the stack. But for now, it'll be on the PHY level. And we hope this will bring the confidence to the adopters of BOW standard. And in terms of to prove the interoperability, we need a platform, right? This all starts with the BOW spec. It's now released 1.0. And we have two startups, Blue Cheetah and T-Matrix. They're doing a test chip for the BOW file they're working on. And then once we take those test chips from these two companies, and then we're developing an open platform consisting of the package, which is what Nadraju and team described, what we call as Interop package. And then we'll also be working on Interop bring up PCB. Once you have package, we also need a PCB to bring up and prove the interoperability. And along with that, we also need a software to drive the test or drive the interoperability test, right? So that constitutes an open platform. And once this platform is available, we'll do the interoperability testing. We are defining the tests. And then, so we'll do the testing and then finally have a report for the community. And so there are several participants in this work, and I like to thank all the people involved here. The Google team has helped us with the initial feasibility study, which helped us going with the layout very quickly. And and then Tisol is working on the package layout, and JSEG will be doing the fabrication and assembly. And you saw on the right side, we have the analog companies working on the test chips, Blue Cheetah, D-Matrix, and Analog Port. And so this is what you saw in detail. I skipped this slide, but later on you can refer to all the test sites. These test sites are actually bring confidence to the developers of BOW standard as well as to adopters. And and it's got various configuration. These configurations are designed based on the use cases, the things that we want to test the interoperability. Right. So, but what I want to focus in today's discussion is really on the bring up PCB. All right. So, so once you have the package, I'm mentioning that we need a PCB. But if you have a test chip like this, the one that we're developing now with a package, what does that look like? This PCB would look like, right? It would consist of power supply, clocks, and CPU or FPGA to stimulate the chip, right? You may want to connect through a JTAG or SPI or I2C interface, access the CSR registers and program it, right? And also you need to monitor for characterization purpose, you need to monitor the voltage, current, and temperature. And there'll be a various clocks and resets. So at the bare minimum, this is what you need, along with the test chip with a socket. And this is what you need. Any test chip bring up vehicle would look like this, right? And maybe there are a few special cases that you want to have based on the test chip, but predominantly this is the architecture for any test chip bring up vehicle, right? And test chip may have a high-speed interface out. In our case, we don't, because all the high-speed interface is limited within the package. But in some cases, let's say if you're developing a SerDes interface, you will have some high-speed interface comes out that can be terminated in a high-speed connector or SMA for instrument access, right? So pretty much I've seen all the people involved in this type of work, all the companies have this very similar architecture, right? And everybody is developing on their own, and it's right. They have their own proprietary implementations. Right. For this work, for the ODSA, what we want to do is actually modularize the split of OCP. We want to modularize this platform for maximum reuse. How we want to modularize this? Split that socket and the test chips on a separate board, what we call a DUT. On the left-hand side, we have what is called a test infrastructure. Right, the test infrastructure is separated on another board, what we call as a test harness. Right, because every design, if you let's say we're coming up with the new test chip design, only the DUT portion is what is different, and the test infrastructure portion, which I call as a test harness, is the same. So how will it look like is like this, right? The test harness PCB will have a programmable power supply, programmable power sequencing, because each of these unlocked chips have got a separate power supply requirements. It can be programmed. And same thing with the clocks. The clock frequency along with the IO standard, if we make it programmable, it's reusable. And again, we have flexible CPU or FPGA to stimulate the chip. And that will be very useful. And same with reset, right? And all in all, if you look at this, it's more or less like resembles an ATE, what is the test harness. If you want to call as a poor man's ATE for a lab bench bring up, this is what it would look like, right? And then on the right side, and what you have is the DUT PCB, which we talked about, which only has the test chip, along with that high-speed interfaces that you want to characterize. Right, and these two PCBs are connected through a kind of high-speed connector, and and it can also be a cable. So it needs to evolve, but bare bones, this is what we want to develop: a reusable bring-up board that can be used by several people, the test harness as well as DUT PCB, right? So what does the usage model look like? Right, so how do you use this? The usage model look like what we have is actually a test harness PCB will be connected to a host computer, say a laptop, running your scripts or running your test code, and they'll be connected remotely via Ethernet or a USB interface. And the host platform will also connect to an instrument via GPIB or USB Ethernet. It can control the temperature, it can set up the test infrastructure, what you need, the host platform in a programmatical fashion, and then it can run the test and collect the data. right? And whole thing can be automated, and that's since we are partitioning the board into multiple modules, and this is something is reusable across companies, across projects, right? So what the benefits we see? The benefits actually it's definitely lead to a lower cost and higher productivity, because we're going to use the test harness PCB across projects, across companies. Only need to develop the small DUT PCB for every project that you're working on. And the other part will become more standard. And this is more like an ATE type approach, right? And also we can standardize the software, right? Most of the time the variable is software, that's what it takes time. And working with the OCP team, there are a lot of expertise, we can take advantage and develop a software that for testing this and can be standardized and open sourced. Right. It also makes this platform, since it's an open platform, if anybody who wants to evaluate your test chip, if you are developing one, it becomes easy for anybody to evaluate. And since we're working on a very standardized platform, right? So there are a lot of benefits working on this. I mean, this is not something new requirement. Every company has got their own approach. What we're seeing is, if can we collaborate and standardize this, so and modelize this part so that the test hardness can be separate from the DUT, and something we can actually share and improve the productivity and lower the cost. Right. So I'll take a pause here. If there are any questions or any suggestions, yeah, please feel free to raise.
The main sense we would like to make is that the PCB on the left should be something anybody who's developing a bow, or I'd say any die-to-die interface. Is that a test packet, a test board will need something like this? JP, can you comment on the performance too that you're targeting? I think there was who was it? It was Kash who had a question on performance at Wednesday's meeting.
Yeah, so I think he was saying about FPGA, right? Connecting FPGA, right? So we can, I mean, depending on the feature that is required, we can definitely make it high speed, passing through the left side to the right side. And also the high speed, most of the time we were interested in high speed for characterization, right? Or if you can connect an FPGA board from the DUT PCB. So I mean, once we define the architecture, we can actually figure out all the details. But high speed is definitely possible, right? And depending on what feature set we want to implement, we can actually either dial down or dial up the cost and the performance.
If you can ask a quick, Mike here.
Sorry, yeah, hi, Mike.
Hi. To a large extent, this looks fairly generic. So where does the actual sort of BOW come in? Is it in the types of tests, the software that you run?
How do we test BOW interface with this infrastructure? Is that the question?
Yeah, because it looks fairly generic to me.
Correct. So let me, good question, Mike. Let me go back to this, the high level picture, the substrate drawing. So what you see here is actually, let's talk about BCA, blue cheetah to D matrix, which is what we're interested in, interoperability. And so in order to set up the test and test the interoperability, right, there is no high-speed interface that comes out. All this high-speed interface are within the package itself. So the way we do it is actually we send some patterns to a SPI port or an I2 JTAG port and store in the chip, and then it has a PRBS generator and validator, right, like a bird kind of interface and the loopback mechanism. Right, all this is programmatically actually set up in the blue cheetah as well as D matrix, and then the one data is transferred, we verify them in the buffer or using PRBS generator. Right, so all the test is contained within the chip itself. So all we need is a JTAG or SPI port access to access the CSR control status registers to monitor the test, execute the test, and monitor the training. All the functionalities of the BOW interface we want to validate is designed such that the test chips are designed such that can be validated through a register access.
Okay. Okay.
Right, pretty much most chips are designed that way, but in some cases we are bringing out a SerDes interface that needs to be come out an SMA connector or a high-speed connector, which can be done flexibly on the DoD test board as well. Right, and so what we need to decide is, I mean, there may be more. What I have captured here is a generic architecture, right? But there may be some few nuances you need, which is that's what we, as an industry, if we discuss, if we define as a common standard for test hardness, it becomes reusable across projects, across companies. And I'm sure this particular test hardness what architecture I have, it would cover about 85 to 90% of the use cases, because this is what you need: GPIO and monitoring capability like ADC tag monitoring capability. Then you need JTAG spike ports, reset clocks, and programmable power supply. This is what you pretty much you need to actually stimulate the chip. Sorry, was there a question?
So JP, just a quick question. So let's just say JTAG as an example, right? So you're gonna want to test this test chip, or let's not call it a test chip. Let's call it a test module, right? Because it's gonna have multiple chips in there.
Right.
So if you just wanted to do JTAG, are you actually using JTAG in this to test the connectivity of each of the chiplets, or
Yeah, so let me go back to this diagram. The blue cheetah actually uses a high-speed JTAG for that for the CSR access, whereas D matrix, I think they have a SPI port and I2C, and they also have an UART.
Okay.
So
those
all
are
this
being actually
we are taking out.
Okay, got it. Okay.
Yeah, so the D matrix have got an embedded CPU, RISC CPU inside, so they have more interfaces, which will all be brought out and connected to our CPU or JTAG on the test hardness PCB, through which we can stimulate the chip or observe it.
Okay, got it. Thank you.
Sure. And so going further, I think we talked about the benefits. The other thing is, yeah, sorry, go ahead.
So can you sort of define, I mean, not now, but we can also define expectations of a test chip, right? Like if it meets, as long as it meets these conditions, it can be used with this with this motherboard with a harness, basically.
Right, exactly. We can define that, yes.
So
I mean,
if somebody's building a test chip, they meet those conditions, they should be able to reuse our harness and the software.
Right. If you're building that test chip for, let's say, analog characterization, a SerDes test chip or equivalent test chip like a chiplet test chip like this, it can be covered 100%, right? But there may be some few corner cases which I don't know what it is, which is what I'm giving the benefit of doubt. But maybe some people have got some special requirements, and that something can be also incorporated if you know what they are. But if you're doing a SerDes interface, chiplet interface, test chip like this, 100% we should be able to work with this architecture. Does that answer the question, Bobby?
Yes, it does. Yeah, thank you.
Okay. Sure. So let's go to the next part. Is really, I mean, we want this to make it as more a community project because the test harness PCB development, right? We need to define the architecture and features. We have some base features required for the architecture required for the bring up PCB we have in mind for the BOW interface, the one we are developing. But I think if you work with the community and if you define a broader set of architecture and features so that for the maximum use across the industry, then it'll be definitely a win-win, right? And once we define this architecture, then comes along with this as a test software. And if we define the APIs, is definitely become standardized bench bring up platform in the lab, right? Just like in ATE, it can be a standard platform for the lab bring up. So that's what we want to get at and invite wide participation to define this whole test harness architecture.
So JP, just going back to that picture of yours.
Yeah.
So if we assume, like, what do you think is the base cost of, I mean, what is the base cost of a test harness PCB and software? What's the base cost of designing your own that customizes that's customized for your package?
Yeah, so really, I'm a little hesitant to give you the answer, Bobby, but I'll give you some rough estimates what I think it is. It could be, right? But it depends on the feature. Let's say if we define all the feature set we want to implement, then we know exactly what the cost. For instance, what kind of power supply, how many channels that we want, and what kind of regulation we require. And what is the power of CPU on, right? And how big the FPGA needs to be. So the cost actually depends on that, right? But to give you a kind of ballpark, I'm estimating it'll be in the order of 75K range, right? But this cost, once we have a partner on board who can do this, they can provide we can figure out the exact cost, just like how we work with Tizol for the package. If we would need somebody to help us from the implementation side, and ODSA will control all the specification and the requirements. Right. And so once we get to that point, we'll be able to know the exact cost. For now, actually, what I think will be in the range of target budget I have in mind, this very crude high level approximation, anywhere from 75 to 100K, depending on what feature set we want to implement. Right. It could be less as well, depending on if the feature set is not, people are not interested, they just want to have something for a low analog chips, simple analog chips, then it could get dialed down as well, right? So, but the numbers I have in mind is anywhere from 75 to 100K, depending on the feature set we want to implement. And for the funding, there's actually the one what we talked about is really crowdsourced through participants. They get the test harness and DUT PCBs in return. And rest of the funding comes from the contribution from hyperscalers, just like what we did for the previous projects, the package and the boards development we had in the past.
But
right?
Our expectation is that if somebody did, in our expectations, there are two assumptions we're making, right? One is anybody building chiplets will need something like this. And the second expectation is that the incremental cost of the DUT PCB is much lower than the cost of the baseboard. Those are the two assumptions we're making.
Yeah, absolutely, Bobby. Yeah, you brought up a good point. This DUT PCB cost is pretty negligible, very small compared to the test harness, right? Is actually most of the cost here. What I'm talking about is NRE, right? Because it's a new development, we need to pay the NRE. But if once it's all standardized, this cost of these PCBs and whole setup can be brought down. And my initial estimation on DUT PCB cost should be less than 10K. Right? It's only the bulk of the cost goes into socket, and how many layers that we need to break out the test chip. But we can figure out the exact cost once we define the feature and the partner we have on board for this development.
And so the reason we're going for this crowdfunding is we're hoping it's in everyone's interest to contribute to the development of the baseboard. And even if they're not participating in the test package and the test chiplet, even if they're building their own system, they can reuse this and just customize it by building their own socket and DUT PCB, right? That's our thinking right now.
Yeah, absolutely, Bobby. Okay, and
we're almost at 9 a.m. Sorry.
Sorry.
Hey, I just wanted to say, JP, great work, all of you. in moving this. This is actually not easy at all what you're doing, especially with the community involved. It's extremely difficult. And this is the second time, JP, under your leadership, you're developing this. You developed the Mara test board, which worked very well. So I just wanted to mention that this is really awesome
Yeah,
work
thank you.
on
Thank you for
you,
supporting all
and you
these
are
projects.
driving it. Yeah, no, and you are the guy driving this. So kudos to you and everybody else.
Yeah, thank you, DJ. Thank you for supporting and Meta supporting through all these projects. Yeah, so and finally want to conclude. I think we are running short of time, but we'll have this scale from the schedule wise. We're doing very good. We'll have the interoperability testing, the whole thing done by Q1 of next year. So we're making very good progress in the package and the PCB, and we'll soon make progress in software as well. And we'll have the interoperability demo by Q1 of next year. Yeah, thank you. So this is what I wanted
JP, thank you. We will come back. We will go to everyone with an actual ask and see if we can raise money for this huge effort. JP's.
So, Bapi, I have an ask for you actually. For the OCP Global Summit,
Yeah.
I was checking the Experience Lab, and I don't see anything on the ODSA side. I know there was stuff presented last year in the Experience Center, not lab, sorry, Experience Center. So this is just a request, Bapi, if ODSA Experience Center can be coordinated at the Global Summit with some of the actual things showcased, if it is possible, that would be a good thing to show.
Yep. All right. JP, thank you as always. This is just wonderful work. That's all, Mike and Nataraju, and thank you too. The progress is very nice.
Yeah. Thank you. Thank you, our support, JP.
Yeah, thank you, everyone. Yeah.
Everybody have a good weekend and everything.
Thank you.
Hey, thank you. Have a good weekend.
Thank you.
Bye.
Thank you. Bye.
Yeah, thank you. Thank you all.